The following is rated TV MALSV. It contains strong language, violence, and nudity. It is intended only for mature audiences. Viewer discretion advised.
Full logic control! Oh, yeah! Ah! Heather, what's logic?
I don't know.
Yeah.
Luckily, Hunter and Kenneth were able to loosely explain what this really means and how it can be applied to real use.
Go! Alright, so, Boolean logic. Logical thinking involving only true and false states. Now, if you look right here, we'll bring the camera, it's also called propositional logic. Wow, that's a lot of lines.
That is called Hertz, and it hurts.
Oh! Alright. It also has and or operators. And it's a type of thinking that's commonly used in basic philosophy and is very useful sometimes to guide thinking. So, right here we have two premises. Premise 1, if it's hot, we are in hell. Premise 2, it is hot. And from those, we can conclude we are in hell, which a statement I think we can all agree is true. Where can I set this down? Fuck. Shit, there we go.
Yeah. Well, you could put it up there. The beach life is for me. You can even put it up there further. There's like that little ledge. Right there. Oh, fuck. Okay. Maybe move. Oh, shit.
What is this made of?
Good question.
Is this still recording?
Yeah.
God damn. Alright, so... distributive rule. You wanna... we'll go to the... there you go. Alright, so... yeah, it's similar to regular algebra. How long is this supposed to be? 5 minutes?
10 to 15.
Okay. Boolean algebra. Alright, back to me. This is sort of a algebra mathematization of Boolean logic, which is used in a lot of philosophy and other sorts of things. Alright, so here we got Boolean algebra. It's basically a mathematization, which is an actual word, fun fact, of Boolean logic, or propositional logic. And it's very similar to actual regular algebra, because it just is. It's just similar. Don't question me. But only if we have or as addition and as multiplication. So we can see that in things like 1 plus or 0 equals 1, which is the same as 1 plus 0 equals 1. Of course, it's different still in some places, such as 1 or 1 equals 1, which is not the same as 1 plus 1 equals 2, because different result. And a pretty decent way to think about that is that every value that's over 1 is basically 1, or true. And there's another symbol, not, that I just learned about. It's basically like a negative sign. So we have x or y and not z, which is the same as x or y and not z, because I just said it out loud. And what's great about Boolean algebra and logic is that it's only one step away from what computers do. If you know anything about computers, they do ones and zeros, little bits. And that is why Boolean algebra and logic are so important to logic gates and computers. Good?
Yeah.
Alright, as you can see here from this lovingly illustrated title, logic gates are abstractions. What does that mean? It means we don't care what's actually inside of them. A logic gate is not an actual physical component. There's no AND gate anywhere in existence. What there actually is there's a switch, or a vacuum tube, or a transistor, or something that actually carries out the functions of a logic gate. The way I like to think of it is like a motor. When we're looking at a physics problem involving a motor, say we have an elevator. It's got to go up by 300 watts. When we're answering that question, we don't care if it's powered by electricity, by gasoline, or by a horse. It does not matter. What matters is the wattage it provides, the function it serves. We put in power, or we put in something, and we get out power. Doesn't matter what comes out, exactly what form it takes. Okay? And now, I'm going to erase this, and with the power of video editing, you don't have to watch me draw all this again. You can press cut, Kenneth. Alright, so as you can see here, through the magic of video editing, you didn't just have to watch me draw that. Logic gates. We have an AND gate, but I forgot to write the word AND. Don't. And we have an AND gate right here. We can do that with switches, we can do it with a transistor, or we can do it with vacuum tubes. I don't know how though. I don't know how to draw that, so just bear with me. And the same goes for all. Shut up, Kenneth. The same goes for all other logic gates. In our computers, usually we use transistors, but in the past we used vacuum tubes, and the diagrams for the logic of that was exactly the same. Because the logic didn't change, even if the method we went about creating it did.
Logic table.
So now you gotta wait for a little bit.
Alright. So, logic gates are based off of Boolean algebra, as Hunter said earlier.
I said that.
And, ways that are, that is shown, not just on a circuit or a diagram, they're shown through truth tables. They can be shown as ons or offs, or yeses or nos.
Or ones and zeros.
Yes, for this video, I decided to use a binary type of table, using zeros as offs, ones as ons. So, for a yes, if the input is a 0, that means that the output would be a 0. If it's off, it's going to be off. And if the input is a 1, that means that the output is also going to be a 1. It's yes is yes. For not
You don't have to explain. You already explained them all.
Okay.
Just look at the table. So you explain them all, and that same sort of pattern follows. So like an AND, it's only on when both of those are on. The pattern follows for all the rest of the tables.
Get the hair off.
Good job, Kenneth.
For OR, if one of the switches are on, or if both switches are on, that means that the switches, or that the output would be a 1. But if both switch 1 and switch 2 are zeros, that means that the output is also going to be a 0. You can notice a pattern for NOR, which is the inverse of OR.
It's the inverse. It's not OR.
Yeah. It is in fact the opposite. You can see 0, 1, 1, 1, 1, 0, 0, 0.
Wow.
Yes. And for NAND, the
Same thing.
inverse of AND,
Yeah, same thing.
it's going to be in fact the same thing. You can see for NAND it is 1, or the output goes as follows: 1, 1, 1, 0, all the way over here. If my computer can do this. You can see that's in fact the opposite: 0, 0, 0, 1.
Wow.
It's pretty cool, man.
Do a little nod thing. All right, that was stupid.
So here's an AND gate, just a small diagram I have sketched on my laptop. I just did a one line type of thing just to make it very simple. Here, right here, is where the battery is. It can be of any kind of voltage, really doesn't matter. Here is the resistor, whether it's a light or just anything in general.
Why does it have to be there?
It can be past the switches, but
Oh, so it's just the output, essentially.
okay. And then here we have 2 switches. Now the difference between an OR and an AND gate is that an OR gate, it can have one of these switches flipped, or this switch can be flipped. But with an AND, this has to be turned on and this one has to be turned on. It can't be where, oh, this one's on and this one's off. That would cut off the current about right here. And if this was off but this was on, the current would be cut off right here. So that just gives you a general kind of picture of what an AND circuit is. All right, here is the diagram for the OR gate. It is very simple, but it's almost exactly like the AND gate in a sense. Not diagram-wise, but whenever you look at the circuitry, it will be. You can see right here, it actually splits off into 2 different switches, which both hit ground. What this allows you to do is for both of these can be turned on, and one of these can be turned on in order for this resistor right here to work, and also for the current to actually flow through the whole thing. So here is a diagram of 2 of the most basic logic gates. One is called NOT and one is called YES. Basically the YES one is if the switch is off, that means that the current will not flow through the whole system. And if the switch is on, that means that the current will flow through the system. NOT gate is the exact opposite. If the switch is off, the current will flow. If the switch is on, the current will not flow. I in fact had to use a relay for to create a combination of both logic gates. And all a relay is a it's an electrically charged switch, unlike a regular physical switch, like these little digital pads down here. Despite me actually having them hooked up, you'll see it whenever I demonstrate it in a like a actual circuitry use. In fact, I'm just gonna go ahead and show you it right now. At least in that portion, anyway. Here's probably the most rough diagram that you will ever see in your entire life of a NAND diagram. Yes, wow is proper.
What does stand for, Ken?
It can be where
Not and.
Yes. Okay. So here we have a battery going to 2 different switches, which this first switch goes down to resistor 1 and then hits ground. Second switch goes down to resistor 2 and ground. It's just to not blow my LED. Same for these 2 resistors over here. This right here is this stands for a transistor. Here is where the power will actually enter the center of the transistor, and power will go out from this first transistor over here, and it will also go out here, kind of like a exit, and over here it will go back into the transistor, and it will go out to a ground. Over here we have current flowing through this other resistor to hit ground, and then we have current going through the LED and hitting ground. Okay, so here is a NOR gate, and as Hunter said,
The pacer test is a multi-stage aerobic capacity test.
okay, that is NOR stands for an inverse OR gate. And it's
Not or.
yes, okay. It's almost like the NAND gate. The only difference is that over here, the exit for the transistor, the exit for a transistor, connect together, and they both go to ground, and both of C's, they come out and they both go to LED. To go ahead and demonstrate these circuits very quickly, I'm just going to go ahead and edit in very short clips of these circuits being used. Here we go and see the AND gate. Whenever I hit switch 1 and switch 2, the LED turns on. Whenever switch 1 and switch 2 aren't pressed together, the LED is off. For the OR gate, once I hit switch 1 or switch 2 or both, or switch 1 and switch 2, the LED turns on. When neither are pressed, neither are on. For the yes and not gate, you can go ahead and see that one of the LEDs are already on whenever I am not pressing switch 1. That means that the NOT gate is working, and whenever I click switch 1, the other LED turns on, which proves that the yes gate is indeed working. For the NOR gate, whenever I hit switch 1 and switch 2, you can see that the LED does not turn on, and whenever I hit switch 1 or switch 2, this switch does not turn on, proving that the NOR gate is in fact working. For the NAND gate, whenever I hit switch 1 and switch 2, the LED is off, but whenever I click switch 1 or switch 2 where I don't have any of them pressed, the LED is working.